So good morning to all of you. In today's class, we are going to discuss non-linear programming problem in which my constraints are of type either less than or greater than. So till now what we have discussed, we have started the NLPP and we have done the search techniques for that, right? We have done that how can we find the approximate solution. Then for the NLPP, we have started without constraint. Without constraint, how do you check? You check the function by the Hessian matrix that it is convex or not. Hessian matrix that is it is positive definite or positive semi-definite, negative definite or in negative semi-definite. Then we come across with constraints, and in the constraints we have done only with the equality sign and we have done the Lagrange multiplier method. In that what you have considered, you consider the Hessian bordered matrix and then you check it is positive. From the starting we take the sign of di and you start from I is equal to 2m plus 1 and m is the number of constraint. Then you check it is alternating the sign or it is preserving the sign as this or it is alternating the sign. Then you can check that it is maxima or minima. In today's class, we are going to discuss when we have constraints either of less than type or greater than equal to 2 type. So first one remark that what I want to tell you, since we are considering the NLPP in this case, so the maximum or minimum which we obtained, right? The maximum or minimum obtained for NLPP can be local instead of global. So you must have heard this word local and global. Local means when I have a function like this, so this is, if I'm considering this interval, this is the maximum value over here. That means this is local minimum, local maximum. But if I'm considering the whole domain from here to here, so this is my global maximum. So it can be possible that when you are solving the problem, the non-linear programming problem, if you obtain maximum or minimum value, that can be local instead of global. But if you check this condition, but if your NLPP is convex programming problem, then surely maximum or minimum is global maximum or minimum. So you got my point. So what is the condition over here? Whatever you are solving, if that programming, because whenever we have to find the optimal solution, we always talk about the global. We cannot fix the domain that this is maximum in this domain, minimum in this domain. So we have to find the maximum which is throughout the maximum from all the possible solution. So if your non-linear programming problem is convex non-linear programming problem, then your obtained maximum or minimum will be surely that will be your global. So since this is a new word, so firstly we will discuss the convex programming problem. Before starting the convex programming problem, I'll tell you what is the convex function. This name convex or concave you have already heard in your first year when you talk about the convexity and concavity. This is the same thing that you discuss, that if you draw a graph like this, right? So what convex means, how many you if you take tangent on this curve, all the tangents will lie below this curve. It will not go beyond up this curve. So the convex function is the same definition that you have earlier done. So in this, how we will check the convex function? So if we are considering, let S is a subset of Rn because we are n-dimensional place and we can have n variables. B convex set, right? from where we have to take the points that should be the convex set, then the function from S to Rn is said to be convex, if it holds this condition that f lambda x1 plus 1 minus lambda x2, it should be less than equal to lambda fx1 plus 1 minus lambda times fx2. Here x1 does not mean this is a 1 point. X1 means because we are n dimensional, that means it is this point x1, x2 and xn. Because this is 1, so I am using the subscript 1 with this, right? X2 can be n dimensional, that is this is the point x1, x2 and xn. Because this is the second point, so I am using this. So this, if you remember this thing, this we have already done in convexity. So what it says, the function is convex if you take the points S from the set S, which is already a convex, and if you apply the function f on n, then this should be less than equal to this. In this, say, when you have inequality less than equal to, then you say it is convex. If you take the inequality only less, then it will be my strictly convex function. So even you can see even if you draw its figure like this. Suppose this is any, we have given any function, right? Suppose we have to check the function, that means this is convex. So what it is saying, so these are my points that I have to consider from the set S. So suppose I am taking this as my x1 point and this is my x2 point. So you can see that this is the value at fx1, right? And this is the value at fx2, right? Now if I join them by a line, right? And the value obviously x1, this is my value x2, the value lambda of x1 plus 1 minus lambda of x2, obviously it will be somewhere this point, because it is a line. If you remember, kya condition lete the hum, that I take the lambda, it is varying from 0 to 1 if I take the CLC. So if we are considering 2 points, it will be in this point, in these 2 points. So if you see, this is my point lambda x1 plus 1 minus lambda x2. And if I apply the function on this value, what is this value? So this is the value at my f of lambda x1 plus 1 minus lambda x2. So this is the value at my f. So this is the value at fx1, this is the value of fx2, and if you join them by a line, this is my line lambda of fx1 plus 1 minus lambda of fx2. So this you can notice that this is somewhere the value, it will be in this interval. So this value is less than equal to this, right? So that means this is my convex function. On the other hand, the concave you can also check. How you will check the concave function? That if you check f of lambda x1 plus 1 minus lambda x2, it will be my greater than equal to lambda times f of x1 plus 1 minus lambda times fx2. So this is my convex. If I take the inequality as only greater, so it will be my strictly concave function. If we have greater than equal to inequality, that means it is my concave function, right? Concave function is just the reverse of that you wrote in this, the figure will be like this, right? So but that means whatever tangents you draw from here, it will be always above the curve. So one thing you can note from here, just a remark or a note, this is very important to note over here. So if you are saying your function is convex, So you can notice here that it can increase from this side, it can increase from this side, from both the side it can increase. For the convex function, you can always have your minimum value. आपको convex function के लिए हमेशा ही आपको minimum value मिलेगी. और अगर आपका concave function है, तो it can go down now towards this. So that means for the concave function, you will always get your maximum value. So this is just the thing to note over here. Whenever any question is given to you, this thing must satisfy that if your objective function is minimization, then your f of function, that means the objective function f of x should be convex. And if the question is given to you f maximize of f of x, then f of x should be concave, right? So this, to prove this mathematically, we can consider that example that you have to check this. You can consider example that check mod of x is convex or not. So one thing you can also note over here, that's this thing. So if your f of x is convex, if f of x is convex, then minus of f of x will be concave, right? And obviously it will hold that if your f of x is concave, then minus of fx will be convex. So now you have to check f of x mod of x is convex or not. So how you can check that? You can take 2 points, that I am taking x1 and x2 be 2 points. Then I take lambda of x1 plus 1 minus lambda of x2. So be the CLC of 2 points. If I am writing CLC, means that it holds the condition that your lambda is satisfying between 0 to 1. Or you can also take lambda 1 x1 plus lambda 2 x2. Then you can say that your lambda 1 plus lambda 2 is 1. And your lambda 1, lambda 2 is greater than equal to 0. Both are fine. So in this, now to check this convexity, I have to prove that this CLC should be less than equal to f of lambda times the CLC of fx1 plus 1 minus lambda times f of x, this 2. That means now I have to apply f on this. So lambda of x1 plus 1 minus lambda of x2. So whenever I have to apply f on the function x, so what it will do, whatever it is in this f, so it will take the mod. So it will be lambda x1 plus 1 minus lambda x. So this will be x2. So now you know the triangular inequality, that your mod of a plus b is always less than equal to mod of a plus mod of b. So that will be less than equal to lambda x1 plus 1 minus lambda x2. And you can also take lambda this out from this, because lambda is lying between 0 to 1, so it is a positive quantity. So you can take out from lambda from the mode. So it is x2. So if you notice that this is nothing but this is f of x1, and this is nothing but this is my f of x2. So you have proved that f of lambda x1 plus 1 minus lambda x2 is less than equal to lambda of fx1 plus 1 minus lambda of f of x2. So that means my f of x is convex function. It is not convex set. Set means it consists of the point. Functions mean the function which you are defining for n variables. Now, since this is, we have proved mathematically, if the term can be complex, that you have to check x1 square plus x2 square plus x3 square, that it is a convex or not. So to prove the mathematically, it will contain the some mathematically square term, then taking lambda out, lambda common, it will be very complex to check. So how you can also check It is not like that you cannot check like you have done in your M1. You can check the convex, but that convexity and concavity you have only done for your two variables, right? That you calculate your AC minus B square and then you check for the maximum and minimum. That you can also do, but that is only for two variables. If you are in n variables, you can also check the convexity by Hessian matrix. If you remember that we have done Hessian matrix, that we can form curl to F by curl matrix. So we can make H as my Hessian matrix. What will be my Hessian matrix? That it is my curl to F by curl x square, curl to F by curl x1, x2, and so on, curl to F by curl x1, curl n, xn, the same curl to F by curl x2, curl x1, curl to F by curl x2 square, and the so on, curl to F by curl x2, curl xn. And if you have n variables, so it will be curl x2, curl xn, curl x1, curl to F by curl xn, curl x2, and this is curl to F by curl xn square. So this will be your Hessian matrix for the given function. Now, how you can check your convexity and concavity? That you will say if H is, if my Hessian matrix H is positive definite or positive semi-definite, you remember positive definite or positive semi-definite, that we take starting from the determinant that my D1 should be greater than 0, then D2 also greater than equal to 0, and so on. So this is positive definite, positive semi-definite, that your first should be greater than 0, the others can be greater than or equal to, right? So if your Hessian matrix, you start from the taking the determinant from the 1 cross 1, 2 cross 2, 3 cross 3, 4 cross 4, and so on. So if you check your Hessian matrix is positive definite or positive semi-definite, then function f of x is, if it is positive definite, then it means it is strictly convex. Or if it is positive semi-definite, then you can just say it is convex. So the function fx is strictly convex or convex function. On the other hand, if you talk about that, if h is negative definite or negative semi-definite, then the function f of x is strictly concave or strictly concave or concave function. So now we need not to check mathematically that you have to take CLC. This is the best way to check, that construct your program, construct your Hessian matrix for the given function, check it is convex or not. So the same that I have told you example, we can go for the example that I have to check f of x. Now here x is x1 square plus x2 square plus x3 square. So that means here x is corresponding to my three variables x1, x2 and x3. So this you have to check is convex or not. So if you check it mathematically, it will be very difficult to check, that you take the CLC, then you take the square and you apply for function, for applying functions. It will be very complex, right? So what I can do, I can construct my Hessian matrix. What is my Hessian matrix? That I can construct, this will be my curl to f by curl x1 square. This will be curl to f by curl x1, curl x2. This will be curl to f by curl x1, x3. This is curl to f by curl x2, curl x1, curl to f by curl x2 square, curl to f by curl x2, curl x3. This is curl to f by curl x3, curl x1. This is curl to f by curl x3, x2. And this is curl to f. That means the partial derivative with respect to, we will take x1 and x2, the double derivative. So if you take If you take the first order derivative with respect to x1, this will be my 2x1. If I again take the derivative, it will be my 0. So the first derivative it will give with respect to 2x2, that will be, it will, if you with respect to 0 x1, this is 0 0. Now this is 0 2 0, that you can evaluate 0 0. This is coming out to be 2. Now we have to check, we have constructed, this is my Hessian matrix. Now what I have to need to check, only I have to check it is positive definite or negative definite, right? So I can check D1. This is my 1 cross 1 matrix. D1 is my 2, so that is my greater than 0. So this is starting that either it can be positive definite, it cannot be negative definite. Why? Because for the negative definite, this should be less than 0. Now D2, I have to take 2 cross 2 determinant, 2 0 0 2. Now if I take, this is coming out to be 4, which is greater than 0. D3, if you take 3 cross 3 determinant, so it is the product of this. This is my 8, which is greater than 0. Now since each di is greater than 0, therefore h is positive definite. Therefore the given function f of x is strictly convex, or you just say convex, it is okay with this, right? It is positive definite, so you can also say it is my strictly convex function. There will not be equality sign. So my f of x is convex. So since, see, it is very easy to check how f of x is convex or not. So you can also check with another example, that if you have to check f of x, that is x1 square minus 2x2 square. Here you can see x is your two variable system, x1 and x2. You can construct your Hessian matrix. So your Hessian matrix is coming out to be here 0 2 0 0 minus 4. You can construct, right? So this is your Hessian matrix. Now what you can do, you can take D1. D1 means 1 cross 1 determinant, so it will be 2. And D2, that means 2 cross 2 determinant, this is my minus 8. Since this is my greater than 0, but this is my less than 0. So for the negatives, my definite D1 should be less than 0. And for the positive definite, my D2, D3, D4 should be greater than 0. Hence, here the H is indefinite, that is neither it is positive definite nor it is negative definite. So H is indefinite, therefore fx is neither convex nor concave. So in this way you have to check. Now we will come towards the NLPP, which we have started, that we have to consider the constraint less than equal to type. So when you will say this is convex programming problem, when you will say your convex programming problem, that if your objective function is, if it is given like this, like minimization of f of x, here x can be n variables, subject to, you have constraint gix, that should be less than, can be equal, can be greater than equal to 0. You can shift it to this side, x is greater than equal to 0. When you will say this is my convex programming problem, now you can notice this is the minimization problem. That means my this function should be convex function. दैट मीन्स अगर आपको कोई प्रोग्रामिंग प्रॉब्लम गिवन है, आप उसका चेक करोगे कि अगर उसका ऑब्जेक्टिव फंक्शन कॉन्वेक्स है, कॉन्वेक्स कैसे चेक करना है, हेशियन मैट्रिक्स से, दैट इट इज पॉजिटिव डेफिनेट और नेगेटिव डेफिनेट. इफ योर फंक्शन इज कॉन्वेक्स एंड द सेट फॉर्म्ड बाय दीज कंस्ट्रेंट, the set formed by these constraints is convex set, then the whole programming problem is your convex programming problem, right? That I can write side, this is my CPP. So if This is convex, the set forms, this is convex set. But if in this case, this is coming out to be your maximum, right? If this is maximize of f of x, the constraint can be the same subject to. These are my constraint. So for the max, what I have told you, there will be always a concave function. So for this should be my concave function. And this set formed that these are my convex set that we have done. If you take 2 points, the line joining between 2 points should lie between this, that means the set. So then you call this is my convex programming problem. The next we are going to do check whether, example, check whether the given problem is convex programming problem or not. Suppose you have given the problem, this is minimization z 4x1 square plus 2x2 square plus x3 square minus 4x1 x2. Subject to you have constraint x1 plus x2 plus x3 is equal to 15. 2x1 minus x2 plus 2x3 equal to 20. X1, x2 and x3 greater than equal to 0. So you have to check this is convex or not. So you know, for this to form the convex set, if you remember, this is the equation of hyperplane. हमने करी थी ना equation of hyperplane that we say ax is equal to d, and we have said that the set formed by the equation of hyperplanes is my convex set. So this is my equation of hyperplane. This is also the equation of hyperplane. So if they form a set, the intersection we have done, this is a convex set, equation of hyperplane. This is the equation of hyperplane. The intersection of two hyperplanes will also be the intersection of two convex, if we say intersection of these two hyperplane, this will be a convex set. Even if you take the inequality here as less than, greater. So we have also done that the closed half spaces are my convex set. So the intersection of convex set will also be a convex set. So in this case, this will form my convex set, right? The rest is to check. This is my minimization function. So for this minimization, this f of x should be convex function. So if you consider the Hessian matrix, this will be come out 8 minus 4 0. This is coming out to be minus 4 4 0 0 0 2. So you can check here a d1 is my 8, which is greater than 0. d2, if you take the determinant 2 cross 2, this will be 16, which will be greater than 0. d3 will coming out to be 32, which is greater than 0. That means my Hessian matrix H is positive definite. If it is positive definite, that means my f of x is convex. So yes, since this function is convex, all the sets are forming, this is my convex set. So that means yes, see, this is convex programming problem, right? So the next which we are going to do, that is the main and most important method that we have to do. That is your non-linear programming problem with inequality constraints. That means you have inequality, you have constraint, you have inequality, either can be less or it can be greater, that you have to check. For this, we will do only the Karush-Kohn-Tucker condition. That is some called it as KKT condition. In some of the books, it is written as only Kohn-Tucker condition, right? So what are that Karush-Kohn-Tucker condition? So whatever you have, right, you can convert the function. If you have any function, right, either it can be minimized. If you have maximized, you can multiply it with the negative sign. I will tell you condition for this minimization. And if you have the constraints, all the constraints are of less than type, right? You can shift the right hand side towards this so that it becomes gix less than equal to 0 and x is your greater than equal to 0. So for applying your Kohn-Tucker condition, the first thing is that your given programming problem should be convex programming problem. If you have convex programming problem, only then you can apply your Karush-Kohn-Tucker condition. If it is not, then you cannot apply. So even in this case, like if you want that this is convex, so you can apply your Karush-Kohn condition in this. So what are your Karush-Kohn condition, KKT condition? That also comes from the Lagrange, that you can convert this less than inequality equal to, आप कैसे ऐड करते थे, प्लस स्लैक वेरिएबल ऐड करके, बट यहाँ पे हम s1 नहीं ऐड करते, we add s1 square. There is a one reason that why we do, because when we take its partial derivative, if we take the partial derivative with respect to s1 and we are not consider square, it will consider just a constant. So for that we consider s1 square. So regardless of that, so what are my KKT conditions? So KKT conditions are for this programming problem. That means if you have all the constraints are of less than type, if it is greater, you can multiply it by negative sign and then convert it into less than equal to 0. If your function is maximization, you can multiply with the minimization. I am telling you the KKT condition for the minimization case, and GIX should be less than equal to 0. So what are the KKT condition that you take? Curl L, you construct here firstly your Lagrange multiplier function Lx lambda. What is your Lx lambda? The same that you consider your f of x plus you take lambda I into gix, that you construct for your Lagrange multiplier. You construct this curl L by curl xi, you take that it should be equal to 0, because whenever we have to find the points, the necessary and sufficient condition for finding the point, जो आप फर्स्ट डेरिवेटिव टेस्ट भी करते थे, आप क्या कहते थे, फर्स्ट पार्शियल डेरिवेटिव आपका क्या होना चाहिए, 0. सो दैट मीन्स कर्ल L by कर्ल xi should be 0. The second, that your lambda I into gix, here I am writing this for I is for the constraints and I am writing j for the variables, right? So here j can be 1, 2 and the number of variables, and here I am denoting with the number of constraints. So lambda I gix minus bi should be equal to 0. That means you consider that your gix should be less than equal to bi, right? The third is, if you are writing here like this, you can write here it as bi, right? So gix minus bi equal to 0, right? You should remember that how we construct the function lambda 1, whenever we have a 2x1 plus 3x2 equal plus that will be equal to 7. So we will consider minus 7 is equal to 0, right? So gix here minus bi should be equal to 0. The third, which condition we have given, that my gix should be less than equal to bi, right? And the fourth, that my all lambda i's should be greater than equal to 0, right? For all I is equal to 1 to n. This is condition on I, this is condition on I, this is condition on I, right? So these are your conditions. So if you have any programming problem that you have minimize f of x, this is gix bi. If you forget this, you can also remember that this condition, this is nothing but delta of f of, when you are considering the partial derivative, right? F of x plus that you consider this is the sum of your constraint. I is equal to 1 to m lambda I gix star that you are calculating at this should be equal to 0, so that you construct your Lagrange function, right? So this should be, these are your 4 conditions. So from these 4 conditions you find the point for the maximization or minimization. So for example, if you have a given a question, now we will solve one question. Example, that you have to solve the following NLPP, which is given as maximization f of x, which is 4x1 plus 6x2 minus 2x1 square minus 2x1 x2 minus 2x2 square plus 49, subject to you have constraint that x1 plus x2 less than equal to 2 and my x1 and x2 are both are greater than 0. So you can see here x is consist of here my 2 variable. So firstly, whenever we have to apply KKT condition for finding the KKT condition, my programming problem should be given to me as your my convex. So you can see this is linear and this is a curve, this is a closed half space, that means the set form, this is my convex set. You can also check this function, right? This, because this is maximum function, if you are checking, then this f of x should be concave, right? That means h should, when you are constructing, then h should be concave. That means h should be negative definite for concavity, right? So but I have told you the condition for your minimization case. So you can convert your function into minimization by taking the negative of f of x. So you will multiply with the negative sign. This will be my minus 4x1 minus 6x2 plus 2x1 square plus 2x1 x2 plus 2x2 square minus 49, subject to I have constraint x1 plus x2 minus 2 less than equal to 0, x1, x2 greater than equal to 0. So the first and the foremost thing, so I have to construct my Lagrange multiplier function Lx lambda. So how I'll create the function minus 4x1 minus 6x2 plus 2x1 square plus 2x1 x2 plus 2x2 square minus 49. Here I have only one constraint plus lambda 1. It will be x1 plus x2 minus 2. Now, what are my KKT conditions? That I have to take curl L by curl x1 equal to 0. I have to take curl L by curl x2 equal to 0. The next condition I have to take, the second is that because we have only one constraint lambda 1, x1 plus x2 minus 2 should be equal to 0. And the third condition is that my x1 plus x2 should be less than equal to bi, that is my 2. And the fourth condition is that my lambda 1 should be greater than equal to 0. Now these are my 4 conditions that you have to check, right? So from this, what you can get, curl L by curl x1 equal to 0, which implies that means you will get minus 4 plus 4x1 plus 2x2 plus lambda 1 equal to 0. When you take curl L by curl x2 equal to 0, it will give you, that means minus 6 plus 4x2 plus 2x1 plus lambda 2 equal to 0. This is my first condition. This is my second, right? Here you have already used 1, 2, 3, 4. You can also use another number. This is 1, right? So here I'm changing 1. This is my 2. This is my third condition and this is my fourth condition. So this I'm saying this from here lambda 1 x1 plus x2 minus 2 should be equal to 0. And here this the condition is x1 plus x2 less than equal to 2. And here my lambda 1 should be greater than equal to 0. So you can always start from this because it has equal to 0. So from the third equation, so when you have third equation that it says lambda 1 x1 plus x2 minus 2 equal to 0. It indicates that either your lambda 1 should be 0 or your x1 plus x2 minus 2 equal to 0. So if I am considering a case that my lambda 1 is 0, so for the first equation, I will have minus 4 plus 4x1 plus 2x2 equal to 0. And for this equation, I have minus 6 plus 4x2 plus 2x1 is equal to 0. So I have two equation in two variables. From this solution, I can get my x1. You can solve this. You will get x1 as your 1 by 3. And you will get x2 as your 4 by 3. If you get this point, it does not mean that you can stop over here. You should substitute this point in other condition that it should satisfy those conditions. So you can verify in this condition that this condition is x. Here it is lambda 1 is greater than equal to 0. That is satisfied that my lambda 1 is 0, which is greater than equal to 0. This is also a condition that 1 by 3 plus 4 by 3, that is coming out to be my 8 by 3. Sorry, 5 by 3. So that means, which is obviously less than equal to 2. That means with this point, this condition is satisfied. So we have also this condition that my x1 plus x2 can be 2. So here from this side, from x1, I have from x1 plus x2 can be 2. So from here you can get x1, that will be 2 minus x2. So if you substitute in 1, this I have put in 1 for the case lambda 1 equal to 0. So if you substitute in 1, so it will be minus 4 plus 4, 2 minus x2 plus 2x2 plus lambda 1 equal to 0. And if you put it in second, and if you solve this equation, this is coming out to be minus 4 plus 8, minus 8 plus 8 minus 4x2 plus if this is 2x2 plus lambda 1. So if you solve, this is coming out to be 4 minus 2x2, this is 2, right? Plus lambda 1 equal to 0. This is my first equation that gave me. If I put it in the second, that my x1 is 2 minus x2. So it will give me condition that my minus 2 plus 2x2 plus lambda 1 equal to 0. So if you solve this equation, because this has two equation in two variables, you can just add this equation, right? This is star and this is double star. If you add this condition, this will be cancelled out. So you will have 4 minus 2, that is my 2 plus 2 lambda 1 is equal to 0, which will give me lambda 1 is equal to minus 1, which I am not supposed to allow, because my this will not satisfy my this condition that my lambda 1 should be greater than 0. That means x1 plus x2 minus 2 is not giving me solution. So only the point you get here is, this is, suppose you get 1 point from here, then you check what point is maximizing. अगर ये आपका lambda 1 positive आ जाता, then you can find x1 and x2 and you can find the value. तब आप अपने ऑब्जेक्टिव फंक्शन में पुट करके देखते कि आपको किसके लिए मिनिमम वैल्यू मिल रही है. But here we have got only 1 point. 1 by 3 and 4 by 3 is the point. So that means this is my optimal solution. And how you will get the optimal value? If you want to find the minimum value, you have to put it in the minimum function. If you want to maximize, you can put it in the maximum function, right? So if you put it in the maximum function, right, it will give you the maximum value. So that you will put x1 as 1 by 3, x2 as 4 by 3. You will get answer as 483 by 9. So this is your optimal value. So this is your answer. So you can also do the question which came in the last year exam. So that the question was that you have value maximize, you have to, the given function was maximize. This question came in the last year exam, that is 10x1 plus 4x2 minus 2x1 square minus x2 square, subject to you have constraint 2x1 plus x2 less than equal to 5, x1 and x2 greater than equal to 0. So for applying your KKT condition, the first thing, this is convex. Yes, this is my convex set. And you can also check that this function will be your concave function. So applying your convexity, you can convert it into minimization z. That will be minus 10x1 minus 4x2 plus 2x1 square plus x2 square. The constraint here will become 2x1 plus x2 minus 5 less than equal to 0, x1 and x2 greater than equal to 0. So you can construct your Lagrange multiplier function Lx lambda, that is coming will be your minus 10x1 minus 4x2 plus 2x1 square plus x2 square plus lambda 1, 2x1 plus x2 minus 5, right? And now you have to these are your this is Lagrange. Next, you have to write the KKT conditions. What will be your KKT conditions? That your curl L by curl x1 should be equal to 0. Curl L by curl x2 should be equal to 0. This is the first condition. The second is that your lambda 1 into 2x1 plus x2 means GIX should be equal to 0. The third is GIX should be less than equal to bi. The fourth is lambda 1 should be greater than equal to 0. So the same here also, you will start from this case that once you take lambda 1 equal to 0 and the other you take lambda 2 equal to 0. So if you have more constraint, that you will take. अगर आपके पास दो constraint होते तो आप यहाँ से दो आपकी condition आ जाती, lambda 1 into g1x minus bi should be equal to 0, lambda 2 g2x minus bi equal to 0. That means you always start from these conditions and you substitute these conditions in other conditions to find the solution, right? In this way, you can go for this. So the same way you will get over here 2 points. One will not satisfy your condition and the 1 point which will satisfy your condition, that if you will solve, you will get x1 as your 11 by 6 and your x2 as your 4 by 3. This is the question of the last year exam. So this you can solve and the maximum value will be your 91 by 6. So this is your optimal solution. You can verify this, right? And the same, if you have two constraints, you can also solve that question, right? You can also solve this question that you have to minimize z minus 2x1 minus x2 subject to you have constraint. Here you have two constraints, x1 minus x2 less than equal to 0 and your x1 square plus x2 square less than equal to 4 and x1 and x2 greater than equal to 0. For applying the KKT condition, you have to check your convexity, right? So this is linear. This is my convex set because this is closed half space. You remember this is a circle with radius 2 and center 0, 0. So this is also my convex set. This will form the intersection of convex set. This is also my convex set. So these sets will form my convex set. And this again, this is the line. You can also check by Hessian matrix. This will be your convex set. You can construct here your Lagrange function that will be minus 2x1 minus x2 plus lambda 1 times x1 minus x2 minus 0. It will be the same plus lambda 2 x1 square plus x2 square minus 4. That will be your construct your this. Now you can write your KKT condition. The first is curl L by curl x1 equal to 0, curl L by curl x2 equal to 0. The second here is the lambda 1 into x1 minus x2 minus 0 should be equal to 0. And here also the second, lambda 2 x1 square plus x2 square minus 4, this also be equal to 0. Third is that your x1 minus x2 less than equal to 0 and x1 square plus x2 square should also be less than equal to 4. And the fourth is lambda 1 and lambda 2 should be greater than equal to 0. So if you solve this condition, you will get here 3 points for x1 and x2. This will be 0, 0. This is coming out to be root 2, 0 and 2. And this is coming out to be root 2, root 2. So you, because your function is minimization, you have 3 points. So you can find the value as minimum value is occurring at this value. So that means this is coming out to be minus 3 root 2 and this is my optimal solution. And this is my optimal value. So if you have more than one values, you have to substitute in the function and you have to check. And this way you will go to check your KKT condition, and you always start from this thing that this is equal to 0. This you find the cases and solve all the case problems. Okay. So this completes your syllabus. Okay. Thank you.